Welcome to this video version of 11.1 to 11.4 notes. What I'm going to do is just briefly introduce you to some formulas for the areas of polygons and then work through the examples. You are welcome to fast forward through the examples that you don't need help on, and then of course you can always pause and rewind those examples that maybe you found more difficult. So first I just want to point out that a lot of this information you already know. I expect that all of these formulas right here are ones that you're very familiar with. What you're going to find in the problems that we do is that we will be applying some of the high school level geometry to these problems. We'll have to use some special right triangles and Pythagorean theorem and some trigonometry to work the problems. These two formulas might be new to you. The area of a rhombus and a kite, a very simple formula. You find it simply by taking 1/2 the product of the diagonals. The area of a square, the area of a circle, this should be familiar to you. What might be new to you, though, is how to find the area of a sector. Now, a sector is just part of a circle. It is the part of the area of the circle that's bounded by 2 radii and then a chord. An arc. So 2 radii and a chord, all this area bounded by those is what we call a sector. It's like a piece of pizza or a piece of pie, so it's a part of the circle. So to find its area, what we're going to do is just take part of the area of a circle. You might recall that when we did arc length, like if we wanted to find the length of this arc, we took a portion of the entire circumference. Well, same idea here. To find the area of the sector, we are going to take a portion of the area of the whole circle. So how do we get that portion? We use the central angle. If this central angle is x degrees, then the area of the sector will be x 3/60 times the area of the circle. And then this formula will also be new to you, area of a regular polygon. I need to introduce you to some vocabulary. The formula is this simple formula, area equals 1/2 little a times capital P. I think it's obvious from the picture that capital P represents the perimeter of the regular polygon. Little a is something that won't be familiar to you, though. That's a segment that's called an apothem. Let me just real quickly draw a regular. I'll just draw another pentagon here. Okay, an apothem is a segment that goes from, here I'm going to make it red, from the center of the vertex, from the center of the polygon to the midpoint of one of its sides and then perpendicular to the side. So that red segment is called an apothem, A-P-O-T-H-E-M, okay? And then another segment vocabulary word that might be new to you is a radius of a polygon. A radius is a segment whose endpoints are the center of the polygon and then a vertex of the polygon. So I drew the radius in blue, so I'll write the word radius in blue. It gets its name because it is also the radius of the circle that would be circumscribed about that polygon. Okay, so more on regular polygons in just a minute, but we're going to go ahead and start with example number 1. Okay, example number 1, we're asked to find the area of a parallelogram. So the formula for the area of a parallelogram is just take the base times the height. Remember that the base and the height must be segments that are perpendicular to each other. So you'll see in the picture that the base of this parallelogram is 17 yards. The height is indicated by this red dotted line. And notice that the height of the parallelogram is also a leg of a 45-45-90 triangle. So this is where your new information that you learned in high school comes in. Remember, the legs of a 45-45-90 triangle are congruent. So if this leg measures 9, then the height also measures 9. So to find the area, then we just take then the base times the height for a total of 153 square yards. Example number 2 is also a parallelogram. So to find its area, we'll take its base times its height. The base is 32, okay? And then the height of this parallelogram is also the long leg of this 30-60-90 right triangle. So notice that the short leg opposite the 30-degree angle is 12 meters. So to find the height, remember to get the long leg of a 30, 60, 90, you take the short leg and multiply it by the square root of 3. And so that's where we got our height. And so to get the area, take base times height, multiply them together, and you get 384 times the square root of 3 meters squared. Example number 3 asks us to find the perimeter and the area of this triangle. So let's start with the area. That's the easy part. So our formula is 1/2 base times height. Remember, base and height have to be perpendicular, and the height of a triangle is the perpendicular distance from a vertex to the line containing the opposite side. So sometimes the height of a triangle is on the outside of the triangle. So we just took 1/2 its base of 19 times its height of 30 and multiplied that together for 285 square inches. And then to find the perimeter, that's the distance around the outside of the triangle. So we needed to find this piece. This side of the blue triangle is also the hypotenuse of this white right triangle. So I was able to use Pythagorean theorem here to find out what C is. It's the square root of 1,629. So the perimeter is 19 plus 41 plus C, which is this crazy radical here. These are unlike terms, kind of like multiplying or trying to add a number and a variable. You can't add these together, so we'll just put parentheses around this whole expression, 60 plus the square root of 1,629, and then put parentheses around that and label it with inches. Example 4 asks us to find the perimeter and the area of this blue triangle. So to find the area, we'll take 1/2 its base times its height. Well, we're given the base of this triangle, but we are not given the height. So to find the height, we use this white right triangle and use the Pythagorean theorem to find that the height of our triangle is square root of 133. So 1/2 base times height, multiply it out, we get 14.5 times the square root of 133 square centimeters. Okay, and then to find the perimeter of the blue triangle, we only know one side. We know, well, now we know two sides. We know the two legs. We know one leg is 29, the other is the square root of 133. So we use the Pythagorean theorem again to find C. So here it is. C turned out to be the square root of 974. So our perimeter isn't a very pretty answer, but we just add the three sides together and then label the units as centimeters. Example 5 is another triangle, and to find its area, we're going to take 1/2 its base times its height. So I want to talk about how I found this height of 9. So let's label the height as H. And what I want you to remember from this year is that, remember in this big right triangle, when the altitude is drawn to the hypotenuse of a right triangle, the measure of that altitude is the geometric mean between the two pieces of the hypotenuse. And the reason why is because these two triangles are similar, and if they're similar, then corresponding sides are proportional. So if we did, say, a short leg to long leg ratio, we'd have H over 27 equals 3 over H, meaning H would occur twice in that proportion along the diagonal. In other words, it is the geometric mean. All right, so when we cross multiply, we get H squared equals 81, so H is 9. All right, and so that's the height of our triangle. Multiply it together, we get 135 square meters for the area. In example 6, we have this problem. We're told that the height of a triangle is 5 centimeters more than its base. So I have drawn a picture of that. I'm going to let B represent the base of this triangle, and then the height is 5 centimeters greater than that, so we're going to express the height in terms of the base. So the height then is base plus 5. Then we're told that the area of a triangle is 52 square centimeters. We're asked to find the base and the height. So let's start with the formula for an area of a triangle. Area equals 1/2 its base times its height. Or in this case, the area is 52, so we can put a 52 in for capital A, and that is equal to 1/2 the base of B times the height of B plus 5. Okay, so at this point I'm going to do a couple of things. Let's get rid of this fraction by multiplying both sides by 2, and then I'm also going to distribute the b. So be careful, I'm going to do 2 steps in one here. Multiplying both sides by 2, I'd get 104 on the left side is equal to, well, the 1/2 is now canceled because I multiplied both sides by 2. Then let's distribute this b, and we get b squared plus 5b. This is going to be a quadratic equation, so let's get it in standard form by getting one side equal to 0. I'll accomplish that by subtracting 104 from both sides. And then this is a trinomial that is factorable, so we can solve this quadratic equation by factoring. I know that my signs are going to be opposite because of, oops, I hit the wrong button, because of this sign tells me we have a negative product, so that means I have opposite signs, so I'm going to put a plus and a minus. And then we need to find factors of 104 that add up to positive 5. And those two numbers would be positive 13 and negative 8, because 13 times negative 8 is negative 104, and 13 plus negative 8 is 5. Then we'll use the zero product property and set each of those factors equal to 0. The only way I can multiply them together and get 0 is if one of them is equal to 0. So b is either negative 13 or b is positive 8. But in this context, even though negative 13 is a perfectly fine algebraic solution to this equation, it doesn't make sense in our context because b, remember, was representing the side of a triangle. And because of the ruler postulate, we know that that number has to be positive. So we're going to toss out this solution and take this one. And so for our base, the base of our triangle then would be 8 centimeters, and the height would be 5 bigger than that, would be 13 centimeters. Okay, example 7 says that one diagonal of a rhombus is twice as long as the other diagonal. Then it says if the area of the rhombus is 169 square inches, what are the lengths of the diagonals? So here's our formula for the area of a rhombus. We just take 1/2 times the product of the two diagonals. And then what I'm going to do is let one diagonal, it says one diagonal is twice as long as the other one. So I'm going to call one diagonal D, and the other one, in terms of this first diagonal, we call it 2D because it's twice as long as the first one. If I multiply these together, 1/2 times 2 cancels out, and D times D is D squared. We're told that the area is 169, so we get 169 equals D squared. That means D is 13. So if one diagonal is 13 and the other one is twice as long, then it would be 26 inches. In example 8, it says find x given that the area of this kite is 92 square feet. So the area of a kite is found by taking 1/2 the product of its diagonals. So we'll put 92 in for area. Is equal to 1/2 times one diagonal is 22 inches. The other one is x. And so we just solve for x, and we get that x is approximately 8.4 inches. Let me box that. Okay, in number 9, we're asked to find x given that the area of this trapezoid is 177 square centimeters. So here's the formula for the area of a trapezoid. Area equals 1/2 its height times the sum of the two bases. So we just plugged in what we're given over here. The area is 177, so that's 1/2 of our height of 13 times the sum of the two bases. So I just multiplied both sides by 2 and then distributed the 13 to get 354 equals 13x plus, oh, that's not 13. Hold on, I need to fix this. Okay, there we go. Just like magic, I fixed the mistake. So when I multiplied 13 times x and 13 times 11, we'd get 13x plus 143. And then here's the rest of the algebra. And x turns out to be approximately 16.2 centimeters. Okay, example 10 asks us to find the area of this kite. To find the area of a kite, we take 1/2 the product of its diagonals. So to find the diagonals, first of all, one thing that's a little bit unclear, this 6 inches refers to this measure right there. Okay, so as you recall, the diagonals of a kite are perpendicular. So if you look at this blue triangle, in the blue triangle we have a hypotenuse of 10, a leg of 6, and we just need to know this leg here. Well, if you recall, and in example 11, we're asked to find, it says find the radius of a circle with area of 95 square meters. So if area is equal to pi times r squared, we're told that the area is 95. We just need to solve for this r. So since r squared is being multiplied by pi, let's divide both sides by pi. And we would get r squared equals 95 divided by pi. To solve for r, we'll take the square root of both sides. And we get that r is equal to, we'll just leave it, I'm going to write the answer up here. R is equal to the square root of 95 over pi, and we're measuring in meters, so that would be meters. The next 3 examples ask us to find the area of a shaded sector, and remember that sector is a portion of the area of a whole circle bounded by 2 radii and an arc. This first example, I'm going to change this central angle to an easier number to work with. We're going to call that central angle 60 degrees. So to find the area, we will take x 3/60ths of pi r squared. That would be a portion of the area of the whole circle. Well, if our central angle measures 60 degrees, then to find the area, we'll take 60 3/60ths. Oops, 60 3/60ths times pi times the radius squared. Now, some of you may have already written down 66 3/60ths reduced to 1/6. And then 4 squared is 16, so we'd have 16 pi times 1/6, which would we can put that 16 pi over 1, divide out a common factor, and we end up with 8 pi over 3. Our unit is in feet, so that would be feet squared for the area of that sector. Okay. To find the area of the next shaded sector, again, I'm going to change that central angle just to give us an easier number to work with. Let's call that central angle 120 degrees. So the area of the sector will be 120 3/60ths of pi times the radius squared. So 120 3/60ths reduces to 1/3, and then 6 squared is 36, so that's 1/3 times 36 pi. So our final answer is 12 pi, because 1/3, of course, is, 12 is 1/3 of 36. We're measuring in meters, so that answer will be in square meters. And then finally, number 14, to find the area of this blue sector, we will take, now, 65 is the white central angle, but we need the area of this whole central angle. So the measure, of that big sector, kind of looks like Pac-Man, doesn't it? Okay, so 360 minus 65, that's a 5, is, let's see, 295. So this big arc, this big central angle is 295 degrees. So to find the area, we're going to take 295 3/60ths times pi times the radius squared. and this numerator and denominator have a common factor of 5, so if we divide that out, we would get 59 over 72 times pi times 121. So we can multiply 59 times 121, and we're going to get 7,139 pi all over 72. Not a very pretty answer, but let's not forget our units. We're measuring in inches. This is an area problem, so that will be in inches squared. So now we come to the portion of our notes where we're going to find the area of some regular polygons. So that formula, you remember, is area equals 1/2 little a times capital P, where little a stands for the apothem and capital P stands for the perimeter. So let's draw an apothem. So find what looks like the center of your regular polygon, and we're going to draw a segment to the midpoint of a side, and it's going to be perpendicular to that side. Now what we're also going to draw is a radius, because what we can do then is we can use this right triangle to help us find the apothem. We're going to know the perimeter because it's a regular polygon, so the perimeter is going to be 4 plus 4 plus 4. The work is going to be finding this apothem. So to do that, I want to point out that this is a regular polygon. It's a triangle, so each of its angles would measure 60. When I drew this radius, that bisected the 60-degree angle, so that means we have a 30-degree angle right here and a 60-degree angle right there. So we're looking at a 30, 60, 90, where we know this long leg of the 30, 60, 90 triangle, because remember, each side measures 4, and the apothem is drawn to a midpoint, so that means that this is 2 feet, okay? Now, the 2 feet is half of one side of the blue triangle, but it's also the long leg of a 30, 60, 90, okay? So what we need is the short leg, okay? So to get from long leg back to short leg in a 30, 60, 90, remember we take that long leg and we divide it by the square root of 3. And then let's go ahead and rationalize that. So we would get 2, oops, that should be a 3, sorry. 2 square root of 3 all over 3. So our apothem measures 2 square root of 3 over 3. So to find the area, we'll take 1/2 times that apothem of 2 square root of 3 all over, oops, why did I put a 2 here? I'm so sorry. 2 square root of 3 all over 3. Multiply it by the perimeter. The perimeter is going to be 4 plus 4 plus 4, which is 12. All right, and then we'll just simplify here. Let's see, these 2's cancel. 3 goes into 12 4 times, so that leaves 4 times the square root of 3 for our final answer, and our unit is in feet, so that would be in square feet. Okay, our next example is a square, and of course one way to find the area of a square is just to find one of the sides and square it, but I want to practice using this formula for the area of a regular polygon. So first thing I'm going to do is let's actually mark out this 7. I want to write it over here. 7 centimeters is the measure of this radius because it goes from the center to a vertex. What I want you to do is to draw an apothem. Oops, that's supposed to be a straight line. And let's measure that apothem A. And what we're going to do is figure out what the measure of the apothem is. Well, to do that, let's look at this triangle, which would be, remember, this is a right angle being bisected by the radius, so I have a 45-degree angle here, a 90-degree angle here, so that makes this a 45-degree angle. So we've got a 45, 45, 90 triangle where we know the hypotenuse, and what we want to know is one of the legs. Well, remember, in the 45, 45, 90 triangle, the hypotenuse is equal to one of the legs times the square root of 2. So if we're going to work backwards, we're going to take that 7 and divide it by the square root of 2. Let's rationalize the denominator. So we'd have 7 square root of 2 over 2. And that is the measure of our apothem, 7 square root of 2 all over 2. Now, that also, since this triangle is isosceles, that's also the measure of 1/2 of one side, okay? I kind of wish I wouldn't have put that work right there. So 1/2 of one side is 7 squared root of 2 over 2. So we can start filling in here. To find the area, we're going to take 1/2. The apothem is 7 squared root of 2 over 2. And then the perimeter would be this number times 8, right? Because that's half of one side. So if we multiply by 8, we'd have the entire perimeter. So that would give us, let's see, 2 goes into 2 once and 8 4 times. So that would give us 28 times the square root of 2 would be our perimeter. 28 times the square root of 2, and then we just need to simplify all that. Let's see, 2 times 2 is 4, which goes into 28 7 times. So I'm going to do this in a couple steps. So we'd have 49 times. When I take the square root of 2 times the square root of 2, that's going to give me 2. So times 2, and 49 times 2 is 98 square centimeters. Okay, I'm going to skip number 17 for just a minute. Let's do 18 and then we'll go back to number 17. So 18 is a regular hexagon, and to find its area, we're going to take 1/2 its apothem times its perimeter, but you'll notice the only thing that we're given is a radius. So what we're going to do is go ahead and draw that apothem, and we're going to use a right triangle again to figure out the apothem. We'll call it A, and also to find this piece, which is half of one side of the entire perimeter. So let's figure out what kind of a triangle we're looking at here. Well, if I were to draw another radius, then what we would have right here would be a central angle. Now, since this is a hexagon, that means that there would be 6 of those central angles. So if I take 360 and divide it by 6, then this central angle is 60 degrees. The apothem bisects that. That makes this angle a 30-degree angle, which would make the bottom angle a 60-degree angle. So we're looking at a 30, 60, 90, where we know the hypotenuse. Okay, now remember, in a 30, 60, 90, the hypotenuse is twice the short leg. This is the short leg because it's opposite the 30-degree angle. So that means this short leg is 7, and then the long leg, which is also our apothem, is 7 times the square root of 3. So to find the area, we'll take 1/2, sorry, my stylus keeps squeaking, times the apothem, which is 7 times the square root of 3, and then the perimeter, 7 is half of one side, so that means if we take 7 times 12, that'll give us the whole perimeter. 7 times 12 is 84. All right, so multiply that all out, and we would get 294 times the square root of 3 square feet for our area. Okay, so last but not least, let's find the area of this regular octagon. So again, to find its area, we'll take 1/2 its apothem times its perimeter. So you'll notice that in this problem, we're given the apothem. We just need to find the perimeter. All right, so to do that, let's go ahead and draw a radius and create a right triangle. Now, this will not be a special right triangle. Let me go ahead and draw another radius to create a central angle here. And you'll notice that this central angle, there would be 8 of them. So if I take 360 and divide it by 8, I get 45 degrees. So the measure of this central angle is 45 degrees, but the apothem bisects that angle. So that makes this angle a 22.5 degree angle. So what we're going to do is we're going to find this side by using a trig ratio. Now I'm going to write, I'll just write it down here. Remember SOHCAHTOA, our trig ratios. SOHCAHTOA helps us remember that, that the sine is found by taking the ratio of opposite over hypotenuse. Cosine we find by taking the adjacent side over the hypotenuse, and then tangent is opposite over adjacent. So with respect to this 22.5 degree angle, we are looking for, this would be the opposite side, this is the opposite side, and the apothem is the adjacent side. So opposite, adjacent, you should be thinking tangent. So we're going to take the tangent of that 22.5 degree angle and set it equal to the opposite side, which we don't know. Why don't we call that x? So that would be x over the adjacent side of 8. And then to solve this equation for x, we would multiply both sides by 8. So grab a calculator, make sure you have it in degree mode, and you're going to take 8 times tangent of 22.5, and you should get approximately 3.3. So x is approximately 3.3. Okay, so we'll use that 3.3 then to find the perimeter of the entire octagon. 3.3, we'd have to multiply it by 16. And 3.3 times 16 is 52.8. And then let's multiply that all together. Let's see. 4 times 52.8 is 211.2. We're measuring in inches, so that would be square inches. Okay, if you have any questions at all over any of these examples, be sure and ask me in class, and I will see you then.